good? I think that's good.
Can everyone see okay? See their notes, see the screen? Good? Awesome. Okay, so we're going to start with just a basic overview of big O, omega, and theta to make sure that we're all on the same page in terms of concepts that we can approach these homework problems in a knowledgeable manner. So you've probably heard these before, but just double checking that we are comfortable with these definitions. So we can say a function f of n is in the set big O of g of n if for some constant c in all n greater than n naught, f of n is going to be less than or equal to the constant c multiplied g of n. That sounds like kind of a formulaic gibberish, but in other words, we know that the function f of n will not grow faster than g of n as the size of the input, denoted by n, gets large. So for big O, we can look at that as an upper bound on a function. So that is denoted in this figure. Can I draw on here? So this is our big O. So we see that the f of n is upper bounded by the constant multiplied by g of n, so it is within that set. Similarly, for big omega, we can view that as a lower bound. So same goes for the constant c in all n greater than n naught. We know that our function will be greater than or equal to our constant multiplied by g of n. And then we have the combination of big O and big omega as big theta. So that is satisfying both conditions, which leaves us with just an equals. So that is saying that our function f of n is in the set big theta if it grows equally as fast as g of n multiplied by some constant. So you can think of the theta as like the tightest restriction, and then big O and big omega as your upper and lower bound respectively. And just a little note on little o and little omega. You can think of these as the more exclusive bounds because it means that your function is strictly lower or strictly greater than. And just kind of a concept check. Does anyone know why you never hear anyone talking about little theta? Maybe, maybe not. Yeah? Yeah, you're definitely on the right set. So if we have little theta, that means, or that is not very meaningful because nothing would be in it. Because you have the strictest bound upper, strictest bound lower, that doesn't leave us with anything left. So that is just why you don't hear anything about that, and hopefully that kind of clears some things up. So in your homework and in class, you're going to be going through examples of proving whether or not a recurrence relation is within a set. That could be like big O of a function, big omega, something like that, or little o conversely. So we can go through just a couple examples, one of which we are proving that a recurrence relation is in the set, and then we'll do another one where we can kind of have an intuition that it won't be in the set, but we're going to show formally. So when we see this sort of problem, we can ask ourselves whether or not we can find the constant c in an n naught such that this inequality will hold. And if we can find those values, that means that we have shown that the recurrence relation is in the set. Similarly, if we cannot find such a value, then we prove that it will not be in the set. So a good strategy for some of these is to write our problem in terms of like the inequality shaped like here. So when we do that, we have like n cubed plus 20n plus 1. It's going to be less than or equal to c n cubed. And we can simplify this inequality by dividing by n cubed, and that is going to leave us here. So this is where we want to kind of interpret this inequality and think about whether or not we can assign values for c in n naught such that it will hold true for all n greater than n naught. So if we're looking here, we can see that if we choose n naught to be 1 and c to be 22, so that means we have 1 plus 20 over 1 plus 1 over 1 is less than or equal to c. We view that we can assign c to be 22. and the equation will hold. So for this case, we see that the recurrence n cubed plus 20n plus 1 is in fact in the set big O of n cubed. And just kind of a concept question, can anyone think of what would happen when we increase n naught? What would that do to this inequality that we wrote here? Yeah.
I just inverged one.
Mm-hmm. Yeah, so we would need smaller and smaller c's.
Yeah.
And so that we can observe that we can shift around c and n naught, but by choosing a single pair of them, we show that the function is in fact in the set big O of n cubed. So let's move on to an example where we can probably get an intuition that it will not belong in the set, but for our practice and exercises, we want to make sure we can show it formally. So if we have the recurrence relation T of n equals n cubed plus 20n plus 1, we kind of see right off the bat that it's probably not going to be in the set big O of n cubed, big O of n squared, because a cubic function will grow faster than the quadratic. So we kind of see that right off the bat, but we can do the similar strategy we had before to show so formally. So if we do the same step of dividing our inequality, this time it'll be by n squared, since that is the set we're trying to show. So this, we write it formally here. So that is showing that our recurrence relation needs to be less than our constant c multiplied by the function we're trying to show, bounded by the big O. So we divide by n squared, and that leaves us here. Should space this out. Now, this is different from our equation up here. A subtle difference, but we see that whereas here we can have c be a constant factor, is there such a c that we can assign such that it will always be greater as n increases for this equation that is right here? No, because whatever c we choose, as n increases, it will still surpass it. So since that violates an inequality, we can't choose our pair. We then say that the recurrence relation n cubed plus 20n plus 1 is not in the set big O of n squared. So that gets us through the recurrence relations and big O.
So
Raise our hand here if you started on the homework writer. Okay, piece of number. Definitely at least read through it and start thinking about some of the problems, because it can take a while. So.
okay, so moving on a little bit, now we're going to talk about divide and conquer for a couple minutes, which is basically divide and conquer is an algorithmic technique based around taking a hard problem and turning it into like multiple smaller, easier subproblems. There's three steps to it, as can be seen here: divide, conquer, and combine. It's fairly intuitive, but we just wanted to recap this, go over to make sure you were clear, because it's going to come up in the homework, and it's useful to be able to think about things this way. So going into the steps, right? Logically, we have a divide step. So in this thing, we want to break this problem up into smaller problems that we can solve. So divide step is basically just doing that, making it into small problems. Conquer, there's two cases. So when you think divide and conquer, you want to think recursion. You're breaking this into smaller subproblems that you're going to solve each of them in turn, which, as we know, is a recursive problem. So you have two cases for conquer. One, if you have a quote-unquote large subproblem, and B, when you have a quote-unquote small subproblem. So a little out of order here. Small subproblems is going to be a recursive base case. That's when you get down to n equals 1, n equals 2, something like that. You're going to be able to just solve that out of hand. It's easy enough complexity-wise. If your case is large, again, you're going to want to make your recursive step and make that subproblem smaller yet again until you hit your base case. That's just basically recursion. Finally, again, recursion you're going to have to combine. So you're going to take these solutions to these smaller subproblems that you've created, and you're going to just merge them back into one solution for the whole problem, which is going to be the runtime of the recurrence that you're trying to solve. So moving into runtimes, the runtime of a recurrence, which you've gone through in class, and I think we'll define officially here again in the next section, but basically this is the form of a recurrence here for a divide and conquer problem, where T of n is the recurrence for the whole problem. D of n is the runtime of your divide step. This A T of n over b mess is the runtime of solving A subproblems over size n over b recursively. So that's your recursive step, making each subproblem smaller and solving A of them. That's kind of how that works. And then C of n is the runtime of combining the subproblems back in to get your final solution. And so you have to do each of these things. Each of these things are going to be a certain runtime, so they all kind of count towards your final runtime. So to that end, we're going to go through a brief example here just to kind of get you in the how to think about these recurrences using an example merge sort that you should all be very familiar with. So who can tell me what the divide step in merge sort is? So what do we do? Yeah. Right, so we're going to take an n element list and turn it into 2n over 2 element lists, right? So you're just breaking the problem into two smaller problems that are each the same. That's our divide step. So how does our conquer step, so how does our recursion work in merge sort? Anybody just briefly, one of the cases, something like that? Yeah.
Like, so you have like the base case of 1, which is sorted.
So if n equals 1, then you have a sorted list of size 1. So if n is, so if n is greater than 1, what do you do? Again, you sort recursively, right? So you keep breaking it down until you hit your base case. It's, just recursion. You should have gone through this in one of the last homeworks. So then on to our combine step here. So what do we do in our combine step? So in merge sort, this is our merge kind of thing. So anybody want to explain what this does? Right, you're going to take all of your sorted sublists together. You're just going to merge all of those sorted sublists back together until you get one final sorted list. And that's how merge sort works. So now that we've kind of established what each step here is doing, let's look at the runtimes. So in terms of merge sort, right, we're looking at runtime in terms of the number of comparisons that we're doing between elements here. So in order to think about the runtime, it's beneficial to figure out how many comparisons you're doing at each step in order to write out this recurrence. So how many recurrences are we doing in our divide step? Well, all we're doing is we're taking this set, going in the middle and saying, all right, let's chop it in half. So we're not comparing any elements there. So we have 0 comparisons. So for our conquer step, what are we doing? We're going through and recursing down each half of our previous array, which the size of that is going to be n over 2. And then our combined step. Again, how many comparisons are we doing with combined? Well, we have each of our sorted, our size 1 sorted list that we're combining back in. We have to sort every one of those back in. So in this case, we're going to be doing n comparisons. So if we want to write this out into a recurrence of the fashion that we've seen before, we have T of n equals, so we look at our D of n. We're doing 0 comparisons, so we're not doing anything that's really affecting our runtime of merge sort in this step. So it's not relevant to the recurrence here. So then we look at what we're doing in our conquer step. So recurrence is a way of redefining the problem in terms of itself, kind of. So what we're doing is we're taking the original problem, splitting it in half. So T of n over 2, so that's saying do the original problem but half of it, but we're doing it twice. So it's 2T of n over 2. And so then we want to look at our combined step. So we're doing n comparisons in this combined step, so it's just n. So this is the recurrence of merge sort, and I believe later on we're going to get to this in how to use the master method on this. Any questions relating to how we got this recurrence, how we explained everything? Yeah.
Yeah, so when we looked at the examples for like the recurrent stuff in lecture, the D of n part was never there. Like, should we expect that to be on like any test problems or anything?
So one of the things we'll kind of get this in the master method. In order to use the master method, your recurrence has to be of a certain form. I feel like for the most part, it shouldn't have to.
Yeah. Usually people don't write D of n because you can kind of combine D of n and C of n into just one function, f of n. So you don't have to write it like this, and we won't expect you to write it like this on a test or anything.
Yeah.
Dr. Grimm did that in lecture because it's kind of it's trivial, like that would agree with your understanding. So we're doing it to be rigorous and make sure we give you guys the complete information, but I wouldn't sweat as much.
Is the 2 just based on the fact that you're doing like doing on grade?
Yes. So so the recurrence is like defining itself in terms of itself. So you have T of n over 2 is saying I'm doing this like this same thing on half of it. But because we're doing it on both halves, it's 2 times doing it on half of it. Okay. I do a lot of switching here. I didn't think that through. Yeah, because.
Okay. So we've looked at a lot of recurrences so far, but let's actually define it. A recurrence is just an expression for some complexity in terms of itself. So here's a couple of recurrences. The T of n refers to time. So that's expressing some sort of runtime complexity in terms of itself. You can see the expression for that runtime has the function t in it, so that's a recurrence. And S here is representing space. This is a space complexity recurrence. You can do this stuff for space too. The problem is that looking at these recurrences, it's very hard to tell actually how fast these things go, right? I mean, what is that big O of? I have no idea. So what we want is some way of looking at these recurrences and figuring out some easier to understand function that they're big O of. And in fact, it'd be really nice if we knew what they were big theta of, because then we'll have a tight bound on those runtimes. One way to do that, and probably the usually easiest way to do it, is the master method. The master method involves this form. It only works when you can put your recurrence in this form. If you can't put it in this form, you can't use the master method. And this form says that the recurrence is multiplied by some factor A, and then the size of your subproblems is smaller by some divisor B. And then for each time we recurse, we do some f of n amount of work. So you have to look for this form. But if you can find this form, then you can use the master method. And fun fact, all divide and conquer algorithms follow this form. And the proof is really easy. Does anybody want to give the proof? It's one line. It's a one-line proof. No? Okay. The proof is let f of n be d of n plus c of n. So this gets into what you were saying. Usually people don't write d of n and c of n because you can just add them together to get this new function f of n. But then if you do that, then we've condensed the recurrence into that form. So if you're doing divide and conquer, you're probably going to be using the master method to prove the runtime of your divide and conquer algorithm. Any questions so far about the form that you have to look for? Yeah.
If I have a constant in my n over b, like n over b plus 17, does that constant affect my ability to use this form?
So Rohit here is asking if we had a of t of n over b plus 17. Is that what you're saying?
17 outside.
17 outside?
Like outside the plus. Like outside the fraction, sorry.
B plus 17 here, right? Technically, this breaks the master method. Now we don't have a constant divisor here. But we'll learn some other techniques later to get around problems like this. But for now, this does break the master method. Okay? One thing to note, though, is that because this is a constant here, plus 17, it's probably not going to have an effect on the runtime. So it could be worth just to, out of curiosity, prove it without the 17 there and just see what you get. Because usually, if we have a constant here, it's not going to make a difference. But you can't count on that, so this does break the master method. Other questions about the form? One thing to note here is that a and b have to be constants. So if a is n, that's not the master method. That's something else. If b is, log n, that's not the master method. These have to be numbers. 1, 2, pi, something like that. Okay? F of n can be a function of n, though. That can be anything. That could be log n and whatever. Okay. If we put it in this form, then there's a couple of things we can check. And they all have to do with comparing f of n to n to the log base b of a. Okay? All right. So now I understand that in lecture, you guys maybe might have learned slightly different cases for the master method. The cases that you guys learned in lecture are special cases of these general cases. And so I like to just put it all down on paper because once you start using too many special cases, you can get yourself into trouble. So it's nice to know how to do these problems the general way. And the general way is what I'm about to present. And this is also what you find on Wikipedia, etc. So this is the good way to know. And what we're doing is we're comparing f of n to n to the log base b of a. Just intuitively, what are the three possible ways that this comparison could go? Yeah.
Less than 2 and 3.
Exactly, yeah. We're comparing two things. What are the three possibilities? Less than, equal to, or greater than. However, that doesn't quite work because we're dealing with functions here. So what does it mean to say that this function is less than that other function? It doesn't really mean much. We'd have to actually plug in values to say that. So instead what we're going to say is big O, big theta, or big omega. That's how we're going to talk about comparing functions. So case 1, less than. We can't say less than, but what can we say? We can say big O. Okay? So this case says that f of n is big O of n to the log base b of a minus some epsilon here for epsilon greater than 0. What does that mean? That means that f of n grows slower than n to the log base b of a by some polynomial amount. Okay? So let's just see an example here. Like what if f of n is n squared and log base b of a is 2.1. this would be an example of that case, because n squared grows slower than n to the 2.1 by an epsilon equal to, I'm on eraser, equal to 0.1, right? If we take log n to the log base b of a, n to the 2.1, and we subtract epsilon from 2.1, and we set epsilon to 0.1, then we would get 2. And n squared is big O of n to the 2. So this is an example of that case. Questions about that? Okay. If we find ourselves in this case, we get to infer something. We get to know something. And what we get to know is that T of n is big theta of n to the log base b of a. That's pretty cool, because now we have a big theta bound on this recurrence that at first was very hard to interpret. So, all right, let's see an example.
I can just hold that in my hand.
I'll just make it horizontal again.
All right, so we're gonna step through a simple example of that here. You guys are gonna help me out because it's pretty easy. In this, so our recurrence relation is T of n equals 2T of n over 2 plus 1. We're using this as our template. So what's f of n gonna be? Right, 1. Our a is gonna be what? Good. Our b? And log to the base b of a, so log to the base 2 of 2. Right, 1. So now, what we're going to do, compare f of n to n to the log base b of a. So we have 1. We're comparing that to n to the 1. We're in case 1, and we see that 1, so we want to check, that 1 is big O of n to the 1 minus epsilon. That's not an epsilon. And so here we can see, well, we can pick an epsilon and just say anything pretty much between 0 and 1, and then that work out. So let's say epsilon equals 1/2, and then we get, this becomes O of n to the 1/2. 1 is big O of that. Checks out, right? 1's always going to be asymptotically slower than root n. That's what that is. And then, so what does this mean, though? We have T of n is now going to be theta of n to the log base b of a, which is, as we said earlier, 1. So T of n is big theta of n. And so you get a binary tree traversal. The time that it takes to do that is type-bounded theta of n, right? So that's case 1 of the master theorem, a pretty simple example of that. You want to explain case 2, or?
Yeah, sure. So case 2, remember at the beginning we said our 3 cases are less than, equal to, and greater than. Case 2 is equal to. And also, in case you're wondering, it is probably important to memorize the numbers of the cases. It might sound silly, but people do refer to master method case 3. And you'll be expected to just know, oh, that means the big omega case. So it's worth thinking of it like this. Less than, equal to, greater than, 1, 2, 3. So case 2, equal to. And you can see here, instead of using big O, we're using big theta, which is kind of analogous to equals. And here we're going to say that, in this case, f of n is big theta of n to the log base b of a times log to the power of k of n, where k is some number greater than or equal to 0. If this is true, then we get to imply, we get to infer that T of n is big theta of n to the log base b of a times log to the power of k plus 1 of n. And again, this is the full form of the master theorem. It's a little bit more involved than the n to the c form that you might have done in class, but this will come in handy for things like the homework. Okay, any questions about case 2? You'll note here that k can be 0, so that log might not be there.
Is this recording?
No.
I can just project.
Okay. Do it. Andrew's going no mic, so.
Let me know if you can't hear me in the back, okay? So this one's a little more complicated because of the k, but we're just gonna plug and play our functions and see what happens. What's f of n? Right? What is our a here? Good. Our b? Right? See, this is pretty easy, right? Log base b of a? Right, there we go. So now we want to check this case up here. We want to make sure that f of n is big theta of n to the log base b of a times log to the k of n. So we want to see, is n in theta of n to the 1 times log to the k of n. All right, and so what do you think would be a good value for k here? Say we choose k equals 1, right? N times log of n. Is this true? Is n theta of n log n? Yeah? No, right? So k equals 1 is a bad choice. Anybody suggest a better value for k that we could pick?
K equals 0.
Right, so what happens when we choose k equals 0? We have n is theta of n times log to the 0 of n, which is equal to 1, which is just n is theta of n. Is that true? Right. So our condition is satisfied, and once our condition is satisfied, we go here to find the answer for t of n. We see that t of n is theta of n to the log base b of a, which is 1, times, and this is important, log to the k plus 1 of n, right? So we chose our k equals 0 for this step. And so now k plus 1 is going to be 1, obviously. And then so we get log n, which is, as we know, the runtime of merge sort. See, checks out. The merge sort is theta of n log n, right? Everybody clear on that? Any questions? Great. Case 3.
Oh, there's another example.
Oh, okay, yeah. So we have another example, and this is to, well, we'll see what it's for. Anyway. What's my f of n? Right? And log n. A, our b, and log base b to the a, 1, right? So this one's a little more tricky. Well, not really. I think you guys get the gist by now. But n log n, we want to see if it's back up to here. Theta, the same check. Theta of n to the log base b of a times log to the k of n. N to the log base b of a is 1 times log to the k of n. What do you guys think is a good k for this one? 1, right? Because we can see the same on the left and the right if we make it 1. Theta of n times log n. Good, that all checks out. Now we go back up. We see our condition. T of n is theta of n to the log base b of a times log to the k plus 1 of n. So T of n is big theta of n to the 1 times log squared of n, right? And that's how you solve that recurrence. Any questions about this one? This is just to show you guys a value where k is not equal to 0, so you have the log appearing. Right? Yeah.
In class, I went over like a substitution method
We'll get to that later.
Will that warrant the same answer as this?
It should. Alright.
I wouldn't use the substitution on this recurrence. What would you substitute?
Yes. I don't know, I'm just saying, because the way he did, he would always say set f of n to do the, what do you be substituting as? He said like, or in this case, like, probably said like m equals n log n or something like that. So like a clever way to come up with like, as, he said it was like similar to your substitution.
So if you used substitution like that, if you set m to log of n, you would actually move further away from the master method. You wouldn't be able to use the master method then, because then you would have a log n inside of your recurrence,
Yeah.
and that's not of the form. So if you're already in the form of the master method, use the master method. That should be the first thing you check. If you're not in the form of the master method, then you need to start thinking about substitution, that kind of thing. Yeah.
Alright, that case 3. Cool.
Case 3 is definitely the hardest case. We're up to the greater than case, right? We did less than, equal to, now we're at the greater than. And so corresponding to greater than, we're going to use big omega. And you'll notice that the epsilon is back. What this is saying here, this time it's plus epsilon. That's saying that f of n must grow even faster than n to the log base b of a by some polynomial amount, epsilon. But there's a problem here. This time, if we match this case, it implies nothing. I repeat, if you prove that you're in this case, but then make any conclusion, you've made an incorrect conclusion, because this means nothing. Unless one other thing is true. You have to, if you want to use case 3, you have to also prove this. This is called the regularity condition. It says that a times f of n over b is less than some constant times f of n, where that constant is less than 1. What this basically means intuitively is that the size of the subproblems decreases. Yeah, it's hard to visualize exactly why this is needed. And I'm not going to attempt to prove it, but just remember that you have to prove this in order to, you have to prove that the regularity condition holds. You don't have to prove that you need it. You have to prove that that statement is true for f of n and a and b in order to conclude anything from case 3. But if the regularity condition is true, then you get to conclude this big theta bound. Any questions about case 3 and the regularity condition?
But you have to do like all 3 of the checks if you're not like told which case it is.
Yes, that's a good question. So if you're not told what case your recurrence is, then you have to determine which case it is yourself. And what that's going to involve is essentially checking all 3 cases. But all 3 cases are mutually exclusive. So if you just write down f of n and n to the log base b of a, you should be able to quickly see, oh, is this greater than or less than or equal to n to the log base b of a? And that should guide pretty clearly which case you're going to want to pick. Any other questions about case 3 and the regularity condition? Last case? Okay, cool.
It's example time. F of n? Right. A? Right, a little bit different. B? Good. Log base b of a. What was that? There we go. All right, so we want to check, make sure we're in case 3. F of n, we have n. We want to make sure that we're in big omega of n to the, or 0 plus epsilon. Well, what epsilon value should I pick if I want this to be true? Right? 0 plus epsilon, I want it to be... Okay, so if I say n is in omega of n to the 1, okay? Alright, so, alright, that looks good, right? What if I picked n equals 2? Sorry, not n, epsilon. Would that work? No? Right, because n is lower than n squared. Good. So we know where we are in case 3, because we've picked this epsilon equals 0 such that the condition, yeah, we know we're at least in case 3, because we could pick this epsilon, not 1. Right, and so now that we know that we're in case 3, we have to check this regularity condition. So we want a f n over b to be less than or equal to sum k times f of n. All right, we can substitute all our values in, so this becomes n over 2, right? F of n over b is f of n over 2, so that's just n over 2. We want to make that less than or equal to k times n. What value for k should I pick here? Excuse me? Okay, but so can I pick 2? Why?
It has to be less than 1.
Right, so in this example, I can pick anything in k between 1/2 and 2. Let's just say k equals 1/2.
Between 1/2 and 1.
Sorry, 1/2 and 1. Oh. Yeah, so we've picked our k equals 1/2. Now we have n over 2 is less than or equal to n over 2. That seems legitimate, right? So now that our regularity condition is satisfied, now we know that t of n is in theta f of n, which is equal to theta of n. Everybody get how we got there? Any questions about this specific example? We have another one below it. Okay. F of n? Yep. 15n cubed. Our a is 2. Our b is 2. Log base b to the a is again 1. Yeah, sorry. Let me write that a little neater. 15n cubed. We want to check that that is, go back up. What's the condition? Omega of n to the log base b of a plus some epsilon. Omega of n to the 1 plus epsilon. All right. So what epsilon value can I pick here? Wait, is this a right? Right, so I can pick any epsilon essentially between less than 2 and greater than 0. So we can just let our epsilon equal to 1. And then we have our 15n cubed is going to be in omega of n squared. That's good. Now we want to check a regularity condition. So we have 2 times f of n, which is 15n cubed. Sorry, f of n over b, which would be that would be 2 times 15n cubed over, what am I doing wrong?
I don't know. I lost track.
Okay.
As it goes out. What do we got?
Yeah,
That's right.
so this is going to be, yeah, sorry. It's just 15n cubed over RB, which is 2, right? So these 2's are just going to cancel out. We want to make that less than or equal to k times 15n cubed. So what value of k can I pick? Sorry, greater. Yeah. Cubed less than or equal to k times 15n cubed. I can pick, yeah. So what's going to happen here now? Remember, our k up here is specified to be less than 1, right? So if I pick any value for k less than 1, this inequality will not hold, right? That means in this question, the regularity condition is not satisfied. Right? Wait, do we have a typo?
No, I think that works, right? Just divide both sides by. It definitely holds. Oh, you forgot the over 2. You forgot the over 2.
Wait, it's supposed to be wait, which one?
Oh, wait. Oh, shoot.
No. Hold on. This is supposed to be.
Oh, yeah, you have to plug in.
Yeah, it's going to be 2 times f of n, but we're plugging in n over b, right? So it's going to be, okay, there we go. So it's 2 times, it's 15 n over 2, right? N over 2 cubed.
What?
No, but it's,
No, you can plug in.
We could just describe it.
no, I think it's 15 n over
You'll end up
b
having over 8.
cubed, right?
It is satisfying.
This is better, right?
Yeah, that's satisfiable.
Okay, sorry about that. I just forgot how functions worked for a second there, but back on track now. So this is supposed to be a times f of n over b. F of n over, or a is 2. F of n over b is 15 times n over b cubed. 15 n over b cubed. And we want to make that less than or equal to some k times 15 n cubed, right? This b is a 2. Whoa. All right, so this is 30 n cubed over 8 less than or equal to some k times 15 n cubed, right? We can simplify this a little bit, make that 15 and 4. And so here right away we can see we can make k equal to 1/4, and then we have (15 n cubed over 4). This should definitely be is less than or equal to 15 n cubed over 4. Regularity condition is met because our 1/4 is less than 1. We go back up here. What's our condition or our solution? T of n is now theta of f of n. So we get T of n is theta 15n cubed, which is just theta n cubed. Right. Sorry about that. I know that was very confusing, but the issue, I just forgot to plug in the 2 into the cubed. So that's something you should be careful of when you're doing it. As long as you know how functions work properly, that shouldn't be an issue. Sorry about that. But yeah, so this one also works for the master theorem. Okay. Any questions? All right. The
Oh, yeah,
substitution.
Okay, so we just talked for a while about the master method, but there are other ways of looking at recurrences and figuring out their runtimes. And one of those ways is substitution. So I have here a problem that requires substitution. I'm just going to go through solving it. Okay? Substitution is tricky because you have to figure out what you want to substitute. But here, the problem with this recurrence is this square root here, right? The square root is making this so that it doesn't match the master method form. So we're trying to get rid of that square root. One thing we can do is substitute n for 2 to the m. So we're going to just let this be true. We're going to introduce a variable. I think this is a very similar to solving integrals when you introduce a u, where we're performing some sort of substitution that makes the problem easier to solve, just like when you're solving integrals with u substitution. So here we're going to let n be 2 to the n, m, which implies that m is log base 2 of n. Now we can already tell that this is probably a good substitution to make because log base 2 of n is in the recurrence. So sweet. So if this is the substitution we're going to try, the first step is to substitute it. So what are we going to do? We're going to say t of 2 to the m equals 2t to the square root of 2 to the m plus m. Okay? Now, it might not be immediately clear, but we've actually done something really nice here. We've made it so that we can take this 2 to the m and incorporate the square root into it. So we can do this little trick where we have 2 to the m over 2 inside the recurrence. Okay? And that's still equal to t of 2 to the m. Okay? Everybody with me so far? Any questions about the steps that we've done so far? Okay? One thing you might notice here is that what are we plugging into our function t? In both cases, we're plugging in 2 to the something. We're plugging in 2 to the thing. So what we can do is we can define this new function that has that rolled into it, so to speak. So I'm going to define a function s, and it's just going to take in m. And what this will let us do is kind of factor out almost the exponential in the other function called a t. That's a tricky step that we just did there, but the fact that we were plugging in 2 to the thing in every instance of a call to t meant that we could actually define a new function that expects to take in things that are 2 to them. Intuitively. But look, now that we've expressed the recurrence in terms of s and m, we have the master form, master theorem form. So what is a is 2, b is 2, f of n is f of m is m. And I've done a lot of master theorem problems, and so I can just tell you that this is m log n. Okay?
I think you meant S of M.
Oh, yes. Thank you. That should have been an S right there. Yeah. I accidentally wrote T again because I was just copying. But we transformed the whole function into terms of S, and so we need to use S everywhere. Okay? So this means, what are we saying here? We're saying that S of M is in big theta of m log m. Okay? Now all we have to do is substitute back. What was m? M was log base 2 of n. So now all we have to do to find the runtime of n is we substitute back, we get n log n times the log of n. Okay? Does everybody see what I did there? M is equal to m is equal to log n. So this m became that n log n. No, what am I doing? Sorry, yeah, there's no n in front. this m turned into log n, and this log m turned into log of n. And that's it. That's substitution. We've just solved it. Okay? Personally, I find substitution extremely confusing. But this trick of substituting 2 to the m is very common. So it's a good place to start if master method doesn't work. The other place to start would be induction. Rohit.
All right. Are there any questions on what Max just did? Because that was a fairly tricky step you just made. And you will see a test on
Yep.
this.
Yeah, so like you did the substitution with variables, but you also like substitute like functions.
Yeah.
Like, is there like what? So when did you? So like what I'm seeing is this like so s of n, like you put in n for m, you put back like n where the n's are.
Yeah.
But it's still like s of n, isn't it, as opposed to t of n?
I see what you're saying. It comes down to, oh, there's a button on here that changes. That's why it keeps changing to eraser. Sorry. It comes down to the fact that S and T, I believe, are essentially the same function. We're just expecting different values as input.
If I may,
Mhm.
S of m is a wrapper function of T of m. So Max, can you just write out what S what S of m it's equaling its relation to T of m, T of 2 to the m.
What exactly do you mean? Or do you want?
Let me just make this a little more literal.
Oh, this is dead.
So this is a step that Max omitted that I thought we'd get more questions on, but I guess not. But so S of m is equivalent to T of 2 to the m. So when you pass m into S, all S does is hand that forward to T, which takes it in as 2 to the m. So imagine I'm handing it to Max literally. Max takes that and puts it up. What this form of S of m allows us to do is it allows us to apply the master theorem to this function that we otherwise could not apply the master theorem to. So the motivation of substitution is to allow us to reach the master theorem, because the master theorem is a really easy way of improving runtimes with tight bounds.
So yeah, that's what I was saying. S and T are essentially the same function. They just expect different inputs. That's just because we took out all of the exponentials. We kind of factored them out, so to speak. I think of it in terms of that, but yes, technically that's what's going on. We've really just renamed T of 2 to the m. We've renamed it to S. Mm-hmm.
Why is it log n and not log 2?
It is log 2. Well, so actually that brings up a good point. Fun fact, the base of any log in any asymptotic analysis does not matter, because it all comes down to a constant. You might remember from algebra or wherever you learned logs, but log base b of a is equal to log base anything of a over log base anything of b. But this is the change of base formula. You can change the base of any log by just multiplying this by this constant term log base x of b. So it turns out that it doesn't matter. Asymptotically, they're the same. But yes, these would all be 2's because if I had been writing them, that's where we got them from. Yeah. Okay.
All right. Any questions on the material we just covered? Having seen the exam Dr. Graham's written, as of 11 a.m. this morning. I can guarantee you everything we just reviewed is going to be on the exam in some form. So with that in mind, that you'll be testing this material within a couple of weeks, are there any questions you have for us about doing big O analysis of an equation? Yeah.
It's not really like a formal question. It's more like, so the method he taught us in class was like what you guys said was a little bit more informal. So for the write-up, or like just doing all the tests, should we use like this method, like the formal definition, or should we use like what he taught us?
So you can be a little bit more informal on the exam, but we wanted to teach you the more formal method because those kind of allow you to think about things a little more rigorously, which on the homework is going to help you guys add structure to the problem and make the problems easier to solve. So it's not that what Dr. Graham taught you is incorrect, it's that we're teaching you a different form of it, so that way you're able to more easily understand the homework assignment. But on the exam, anything Dr. Graham taught you, that level of formality is going to be okay there. Yeah, it's a good question.
It's useful to know these formal methods because often, if you can see them and know how to use them, they're much easier to write and they're much easier to understand from a grading point of view. So if you write down a tree and try to prove something about the number of nodes of that tree, and it's a complicated tree, it's going to be very hard to actually verify that your proof is correct. Whereas if you just throw down master method case 2, it's very easy to grade, very easy to get points on.
Yeah.
So definitely worth studying these formal methods.
Yeah, I would lean towards the more formal in everything, just because you'd rather be more formal than less formal with something that's more mathematical. That being said, Dr. Graham is great in the exams. He's okay if you use his techniques. So something that I wanted to note on what we're discussing is that with the master method, Andrew was a little bit casual, which is like just because for time's sake, and didn't go through like the rigorous proving that Cameron did for proving recurrence times. So I just wanted to remind everybody that although it's pretty obvious to us that one is in the set of equations that are big O of n to the 1/2, on an exam or on the homework assignment, it would kind of...
That's trivial.
Yeah.
It's trivial,
One to 1/2 is definitely
but I'm just going to warn you that you might lose points on the homework assignment for that, and it'll take you like 2 minutes to do. I'm just saying, make it easy for us to give you points.
If it's close, definitely prove it. If you're unsure, if it's...
I believe it's this. This is
We do
the.
not ask you to prove that.
That's a bad example.
That's trivial. If it's close,
like
if
2
there-
and 2.1
you know, if
or
there's
something.
someone sure, if you aren't 100% sure yourself, that's something you're going to want to prove. If you can look at n squared and n cubed, you're fine.
I just really recommend being as rigorous as possible in the homework assignment, because we want to give you guys points. And we want to make it easy for you guys to get points. So when in doubt, prove it. If it's like a constant within n to the 5, that's okay. But in general, like be formal.
Yeah,
please.
I would say polynomial differences don't need to be proved. So
Right.
if you have like n squared and n to the 2.5, we all know that n squared grows less fast than n to the 2.5. So polynomial differences in asymptotic functions, don't prove it. But if it comes down to like the log of a log, or if it's like powers of logs, or a square root is involved, if there's any doubt, just go ahead and prove it. It doesn't take very long. But definitely polynomial differences. That's where I would draw the line.
That's fair.
Yeah.
That's fair. I'm a little more. I'm less relaxed than Max is. I've gotten burned before, so that's why I'm giving you guys a little bit of heads up there. Okay. Now we're discussing induction. Oh, sorry.
Yeah, so before you said there was a part in the matching theorem form where you could have like a constant inside like the t of n, like t of n over 2 plus 5.
Right.
You said basically the constant doesn't really matter in asymptotic times, so we just prove it using the matching theorem and just say the constant.
As long as you write out this constant will not matter on large inputs, that'll be okay. Good question. All right. Any other questions? Yeah.
So we can't use a tree as a proof?
You can. I'm about to go over that. But a tree is a little clunkier, and the master theorem has been like demonstrated.
It's hard to prove with the tree.
Yeah.
Because you have to prove how big your tree is. You have to prove, you have to prove a lot of things about that tree to actually turn that tree into a proof. And usually, if you're doing a tree, it's possible for you to do one of these other methods, and so we recommend just using these other methods instead.
But yes, definitely, if you can prove all of the necessary parts for a tree, it's valid.
Trees, for the sake of time, we're not going to. We can talk about that later, though.
Just because we discourage it.
It's really like anytime you're using a tree, the master method is, the master theorem is right there for you. And having written a lot of these proofs, the master theorem is much easier to write and solve than the trees are. But if you feel more comfortable with the tree, that's okay.
Yeah.
I might have missed this, but whenever I think one of you guys said that if you have to like minus some constant within the t function, yeah, you had it up above. You said like it wouldn't work. Did we say like what we should do in that case?
So that was the question we said asked up here. I'll just repeat it for you though. On large inputs, constants become trivial. So you can kind of separate out that constant and say, on a sufficiently large input, this constant will no longer affect the asymptotic runtime. So we're gonna discard it for the sake of the proof. We're probably not gonna be that tricky on you, but it's just kind of good to know in the back of your head that the reasoning behind that is, as you have large asymptotic things like in the billions and trillions, those constants no longer affect anything. But yeah. And the way to think about it is if you have n over 2 plus 7, and you have 1 billion over 2 plus 7, the 7 is kind of trivial, and the amount of work you're doing, and does not grow, and 7 does not have any growth associated with it.
That being said, it's not hard to make the constant go away with the other proof techniques we've shown.
Right.
So check to see maybe if there's a substitution you could do or something like that to make the constant go away.
Yeah.
Because the thing is, saying constants don't matter can become very dangerous. Because some constants do matter, like A and B.
Right.
And those are very important constants. So you don't want to just start thinking that constants don't matter, but in this case they don't. But you can do a substitution to make them go away.
All right, so now that we're kind of squaring the material we've covered so far, we're going to discuss proof by induction. Proof by induction is something you guys learned in discrete math, and it's something that was covered. It's covered in theory of computation, and so Dr. Graham says it's covered in 2 courses so far. Didn't feel the need to go over it in class, but it's a useful method. And if you guys are not comfortable with the master theorem or with tree methods, it might be helpful to think about problems in this method, in this way, so that way you're able to solve problems that just through a different lens. So we're going to briefly review induction. This is a block of text. I meant for you guys to read this on your own, so don't worry about I'm not going to read through all of it. But the general sense is, if I have a proof and I can prove that it is true in a case of n equals 1. And if I can take any case n equals k that it's true for and use that to prove another case where n equals k plus 1, where k is in the range from 1 to n, then I have proven it that this theorem works for every intermediary step. So this is kind of tricky notation. What this is saying is that if I prove some base case n equals 1, and if I assume it is true that n equals k, and I've given that assumption, I can prove it's true at n equals k plus 1, then that statement or theorem or algorithm is true for every intermediary step, because if you think about it, I know it's true at n equals 1. If you substitute 1 in for k, you get, if n equals 1, that proves n equals 2. And then since you know n equals 2, if n equals 2, then that implies n equals 3. And you kind of think about that iteratively all the way through until you hit the upper limit, which would be some other n. So that's the intuition behind doing a proof by induction. You prove the base case or base cases, usually just one base case, and then you demonstrate that if you get some element, you can prove the next element. And so by proving that stepwise behavior, you prove it on all elements. So that's the intuition behind an induction proof. This is just like a block of text explaining that in the more formal terms. And if you click on this like on the PDF that we have on Colab, it'll take you to a page with some really good explanations of induction beyond what I'm giving you now. That being said, we're going to apply a proof by induction to merge sort, so that way you guys see an example of it on an algorithm you've seen before, and we're going to prove that merge sort is correct. And a proof of correctness is like really important in algorithms, because if you can't mathematically prove your algorithm is correct, then we can't really have any guarantees about using it. And when you're applying algorithms to real-world applications, having these sort of proofs allows you to apply these functions in really useful ways. So that's why we're having you do this on this assignment. And this isn't just an example I wanted to go through. So my claim is that given a list L of n elements, merge sort correctly sorts the elements L. And I'm going to do a proof by induction. So with the proof by induction, there's kind of two main steps: proving the base case, and then proving that stepwise behavior I demonstrated earlier. So the base case says of merge sort is when n equals 1. And when n equals 1, you have a list of size 1 with one element. So just for example, n sub naught there. So when an array has one element, we know this array is sorted. Is that clear to everybody? Are there any questions on like this fact and how I kind of arrived at that fact? So in the base case of merge sort, we know the list is already sorted. All right, I just want to make sure that was like clear, because just like a regular proof, with the proof by induction, every statement you make has to be rigorously true. And so that's why I wanted to make sure I kind of walked through that. Next is my assumption. I assume that given an array of length L, this should be when that's less than K. I'll fix that. But given an array of length L, for every n, I'll fix it on the board live, that when n that's fine, actually. My apologies. So my assumption for this proof is, given an array of length L, assume that when n is less than k, I can call merge sort on that array of length n, once again, where n is less than k, and merge sort will return the correct output. So from earlier, that's the assumption that I made when I said like if you assume n equals k, prove n equals k plus 1. I'm saying, I'm assuming that when n equals k, I get this behavior. And then, when n equals k plus 1, well, with merge sort, as we went over earlier, it divides the array in two and recursively calls itself on those two subarrays. And I know that those subarrays are of size k plus 1 over 2. And k plus 1 over 2 is less than k. And from my assumption, I know that merge sort will correctly sort those two arrays. So what we have now with merge sort is we've proven that when you call an array of size k plus 1, its two subarrays are sorted. So now if I can prove that the merge step of merge sort is mathematically correct, then I've proven that on any arbitrary k, on any arbitrary array, merge sort will be factually correct. Sorry, will be mathematically rigorous and correct. So when each subarray is sorted, what happens is with merge sort is we call the minimum spot on each array, the front of the array, and we compare the two elements. And we know that those two elements are the minimum of each array. And so then we just pop off those minimum elements and we put it on our new final list. And then we compare, and then we go back to the two lists, which are still in sorted order. We pop off their first two elements. In the case of one list, it'll be the same element as before. In the case of the other list, it'll be a different element than the one we just popped off. Okay. And this process repeats until we sort the entire array. And so, because merge sort's merge function mathematically correctly will merge two sorted arrays into one larger sorted array, then we've demonstrated that that given that n sorts k, n will sort k plus 1. And with our base case, that means when n equals 1, then merge sort will correctly sort n equals 2. And this stepwise behavior continues all the way to n equals an array of arbitrary length.